Hi everyone. What we're going to do now is move on to chapter 7. In chapter 7, we're going to look at expectation of multiple variables in different circumstances in different ways, okay? Um, so you have seen two random variables, you've seen what a joint distribution is, joint densities, conditional densities, marginal densities, all those different elements of multiple random variables. You've seen that in chapter 6. So now we're going to look at the expectation. Okay, so first just some basic properties in 7.1. So if you have, let's just say, you have a random variable that's less than or equal to a. Okay, so you can say that suppose x is a random variable and with probability 1 it is less than or equal to a. Then what can you tell me about the expected value of x? Well, normally what would be the expected value? It's integral from minus infinity to infinity x times the density of x in the continuous case, and you can do a similar summation for the discrete case. And you know that the random variable x is less than or equal to a with probability 1. So this density is 0 when x is bigger than a, correct? So what you will have is, you could write this as negative infinity to a, x times f of x dx, and this f of x is 0 for x bigger than a, and you know that that is less than or equal to integral from minus infinity to a, x is less than or equal to a, f of x dx, take out the a, oops, but this integral is 1 because this is the integral of the density. You don't need to include from minus infinity to infinity because f of x is 0 for x bigger than a. So this is just 1. So this is a. So you have that if the probability of x less than or equal to a is 1, so that's with probability 1 x is less than or equal to a, then you have that the expected value of x is also less than or equal to a, as you would expect. Okay. Similarly, you can show if you have a random variable x that is between a and b. So the probability of x is less than or probability x being between a and b is 1. So you can think of it as x is always between a and b. Then you must have, in a very similar way you could prove it, that the random variable x has its expectation between a and b. Okay? You can show this in the discrete case, you can show it in the continuous case, just very similar, just like we did it for this continuous case. And here I will write it down in the discrete case. So what is it? The expected value of x, what will this be? This is the sum over all the x's in the range of x, or where the probability of x is equaling little x is positive, x times p of x. Okay, but you know that probability of x being positive is only true when little x is bigger than or equal to a and less than or equal to b. So let's just write it down in the situation. This is bigger than or equal to a, so you can say this is bigger than or equal to a p of x. Now factor out the a and you have summation x p of x bigger than or bigger than 0, and that you know this is 1. So this is a. So you have that the expected value of x is bigger than or equal to a, and similarly sorry. you can show that the expected value of x is less than or equal to b. And you can also write down a proof just like we had above in the situation of x being a continuous random variable. Okay, so it's just something you know when you have a random variable x and you have bounds on it, then you know that its expectation will also obey those bounds. Okay, all right, so that's all that you have in 7.1. And because it's such a short section, I'm not going to make a new video. I'm just going to keep going, and let's move on to 7.2. Okay, now what we're going to look at here is calculating expectations of sums of random variables. All right, so how do we approach that? We will approach the expectations of sums of random variables via looking at how we can write down the expectation of a function of x and y. All right, so first let's look at proposition 2.1. All right, what does that proposition say? It says if x and y have joint probability density function f of xy, then you have that the expectation of g of xy, that is some function of xy, is equal to, just like you would have expected what you had in the discrete case. You have the same kind of definition here in the not in the discrete case, in the single variable case. You have the same kind of definition here in the multiple variable case. This is the double integral of g of xy times the joint density of x and y. Okay, and you have a similar kind of thing. This is the continuous case. And in the discrete case, you have the expectation of g of xy is the double sum over x and y of the joint probability mass function times the function g of xy. Okay, all right, so I'm just going to show you this in the continuous situation. Okay, so where does this come from? Well, there was a little lemma that we had in chapter 5. What did that lemma say? If you have a random variable that is non-negative. Okay, so let's suppose, let's do that. In the case of, let's suppose the function g of xy, this is non-negative. Okay, and what we looked at, the lemma we saw is that if you had a non-negative random variable, then its expected value was the integral from 0 to infinity of the probability that that function was bigger than t dt, and you integrate t going from 0 to infinity. Okay, so this was something we saw in chapter 5. All right, and we're gonna use this. Okay, well, so we're proving this proposition in the case of g of xy being positive. Okay, now let's take a look at this inside. The probability of g of xy being positive. Okay, well, what do you have? What you need to look at is look at the region in the plane where g of xy, not positive, is bigger than t. You have to look at the region in the plane where g of xy is bigger than t and integrate the density of x and y, the joint density of x and y over that region. Okay, so this is the integral over the region in the plane of the density, the joint density of x and y, where g of xy is bigger than t. So we're integrating over x and y. So that's the region in the plane such that g of xy is bigger than t. Correct? Okay. So you're looking for, over here, what are you doing? You're looking at the points x and y, or the subset of R2 where g of xy is bigger than t. Okay, now let's take this and put it into that to write down what the expectation of g of xy is. So you have the expectation of g of xy will be the integral from 0 to infinity of the probability g of xy is bigger than t. So I'm going to now write down this double integral over the region xy such that g of xy is bigger than t. Okay. Of f of xy dy dx dt. All right, so all I did was I plugged in this into the expectation of g of xy from before. All right, and now what do? We'll do a little bit of Calc 3 and we'll change the order of integration. Over here, t goes from 0 to infinity and you're restricting to x and y where g of xy is bigger than t. So what can we do? When we interchange the order, we can have t go from 0 to g of xy and let x and y be anything. Okay, so that's what we'll do. We have x and y be anything. All right, and for each x and y, what kind of t's can you allow? You can let t, I mean, you don't have to worry about t being negative because g of xy is always non-negative. So t goes from 0 to g of xy, okay, and integrate f of xy dt dy dx. All right, okay. So now let's look at the innermost integral, and what do you have? You have integral x, integral y. F of xy has got nothing to do with the variable of integration over here, dt. So I can take it out. I'll take that out. And I have integral 0 to g of xy, 1 dt dy dx. Okay, well, what is this? This is just a simple Calc 1 integral. Integral is t, and then you're evaluating it from g of xy, 0 to g of xy. So you get g of xy minus 0 dy dx. So that is just exactly what you have. The double integral over the whole plane of f of xy times g of xy dy dx. Okay? So that's the expectation of g of xy. And this proof, we've assumed that g of xy is positive. Well, what can you do if e is both negative and positive? Then what you can do is break up the plane into two subsets. Look at the x comma y, so the subset of the plane where g of xy is positive, and look at the subset of the plane where g of xy is negative, okay? And when you're doing the double integral, you can write it down over there as a sum, and in one situation you can introduce a minus with the g of xy inside and a minus outside the integral and just work it out. Then this will work because minus g of xy in the part of the plane where g is negative would be a positive function. Okay? All right, so that tells you when you have a joint random variable, the expected value of a function of the two is the integral. When you have joint random variables, the expectation of a function of the two is just like you have in the single variable case. In the single variable case, you have the expectation of g of x was the integral over r g of x times f of x dx. So the formula for jointly continuous random variables is exactly the same. Okay? All right. So let's take a look at some examples and we'll apply this. Okay. So first let's look at example 2A from the book. Okay. So I'm going to read that out. An accident occurs at a point X that is uniformly distributed on a road of length L. At the time of the accident, an ambulance is at location Y that is also uniformly distributed on the road. Assuming that X and Y are independent, find the expected distance between the ambulance and the point of the accidents. Okay? So, what do you have? X is the point of the accident that's uniformly distributed on the road of length L. Okay, Y is the position of the ambulance that's also uniformly distributed on the road of length L. X and Y are independent. Okay, and they're saying to find the expected distance between the two. So what's the distance between the two? It is the absolute value. So what you're asked is you have to find the expected value of the absolute value of X and Y. Okay, all right. So what do? This is a function, this is your g of x, y. And by the formula we just saw, and of course this is also non-negative, but we know that that formula also holds when it is not just a non-negative function. Okay, so this is your g of xy. So you have to take this g of xy, integrate it against the joint density. Okay, so let's take a look. What is the joint density? You know x and y are independent. That's what you have. So the joint density is the product of the individual densities. Okay, what is the density of x? That is 1 over L when x is between 0 and L. And the density of y is 1 over L when y is between 0 and L. And so the joint density is going to be equal to this when x is between 0 and L and y is between 0 and L, and it's going to be 0 otherwise. Okay, so if you want to draw a little picture, so here's L, here's L. On this region, the joint density is 1 over L squared, and outside of that it is, outside of that it is 0. All right? Okay, so let me just erase this. I want to use that square. Okay. So, here's the line y equals x. All right, so let's write down the formula, expected value of the absolute value of x minus y. It is the integral. I'm just going to write 0 to L because that's where the density is non-zero. 0 to L, 1 over L squared, absolute x minus y, dy dx. Okay, all right. Well, we cannot integrate the absolute value, so just like you did in Calc 3, we're going to parse through this. What do you have? In this bottom region, what will you have? You'll have x is bigger than y, okay? And in this dotted region, y is bigger than x, and over here, x is bigger than y. So that's all you need to do. You just break it up into two different regions, okay? So let's take a look. Here, let's just write this down as 1 over L squared, integral 0 to L, integral 0 to L, absolute x minus y, dy dx. All right? And so let's take a look at this. When y is, or just like you have, when y is between 0 and x is bigger than y. So let's just write that. 0 to x is bigger than y, so it's x minus y. Or when y is from x to L, y is bigger than x, so you have y minus x. That's exactly what would have come up had you just done this double integral using the picture from above. And you have this. Okay? So you can evaluate each one of these insides. And what do you have? This is a dy integral. So you have xy minus y squared over 2, y going from 0 to x, plus, let's do this, y squared over 2 minus xy, y going from x to L, dx. Okay. All right, so let's plug all this in. You'll have x squared minus x squared over 2 minus 0, so you'll have x squared over 2. Over here, you'll have L squared over 2 minus Lx minus x squared over 2 plus x squared. Correct? Okay. Okay, so putting these two together, you have x squared over 2. So when you add it all up, you have 1 over L squared, 0 to L, x squared over 2, x squared over 2. That gives you an x squared, plus L squared over 2 minus Lx dx. And now you can just quickly do this integral, just a simple one. So I just plugged in x equals L and I have this. Okay, so that's gone and the result is L over 3. Okay, so that's the expected distance between the ambulance and the accident. All right, so we just use a simple it was just a simple application of the formula and just being careful about the double integral like you would have done in Calc 3. All right? Okay, so now let's just look at what happens when you have just a simple sum of a function of, a simple sum of two random variables, okay? So let's suppose x and y, we'll just look at the continuous case, and discrete is pretty easy. If x and y are jointly continuous, okay, and you have that e of x and e of y are both finite, okay, and let g of x, y, that's a function of x and y, be x plus y. All right? Okay, then what do you have? Then let's look at what is the expected value of x plus y. All right, well, we're just using x plus y as your g of xy. So just applying the formula, you have your integral over R2, or if you want, write down negative infinity to infinity, negative infinity to infinity of the function g of xy, x plus y, times the joint density f of xy, dy dx or dx dy. Okay, it doesn't matter. All right, and this is a sum, so you can split this up and okay, and now let's write this down as two separate integrals. Okay. And now take a look. What is this? Here you have x times f of xy dx dy, and here you have y times f of xy dx dy. You know what I'm going to do over here is I'm going to switch the order of integration in the first one, okay? Switch order. Okay, and then what do you have? Minus infinity to infinity, minus infinity to infinity, x f of x y dy dx. Okay, and this I'm just gonna leave it as that. And you'll see why in a second, if you haven't already guessed. Okay, now this inside is a dy integral. This is just a function of x alone. Oops. So I can take this out, okay? And I'll have integral negative infinity to infinity. These are my x limits. And now I have integral from minus infinity to infinity f of x y dy and dx. Similarly, I'll have over here by chucking the y out. Okay, what is this? You remember? When you integrate out the y from the joint, when you take the joint density and integrate out the y, what do you get? You get the marginal density of x. So what this whole, that becomes this. So this is minus infinity to infinity x times the marginal density of x. Similarly, this is the integral from minus infinity to infinity. Y times this will be the marginal density of y. And what is this? You know, this is just the expected value of x, and this is just the expected value of y. Okay, so that's nice that the expected value of a sum is just the sum of the expectations, as you would have guessed, even when you're dealing with joint densities. Okay. All right, so like here we're dealing with two different random variables, but you have a joint density. So even in the case of a joint density, you can separate it out then. So I'm just going to write down the conclusion up here. The expectation of x plus y is the expected value of x plus the expected value of y. Okay, and this will come in handy. All right. Okay, and in the discrete case, you can prove it in a very similar way with the double sums. And one of the sums, if you just sum out the x's, you'll get the probability mass function for y and so on. Okay, all right. So now let's take a look at a couple more examples. If we look at example 2c, we're going to look at a mean of n random variables. Okay, so example 2. Okay, so what do you have in this example? You have n independent random variables with the identical distribution. So what does this mean? Every single one of these n random variables, firstly, they're all independent. And every single one, they all have the exact same probability mass function, distribution function, mean. They all have the same density, distribution, mean, so on. So it's exactly the same. They're all normal with mean 3 and variance 12, or they're all binomial random variables with n equals 14 and p equals 0.9, or whatever you have. They're all identical, but they're independent. All right? So what you have is you look at the quantity x bar, which is the sum I going from 1 to n of the sum of these So it's the sum of Xi's over n. Okay. Anyway, in this case, you say the sequence is said to constitute a sample. This is, you say the sequence is making up a sample from the distribution F. All right. So this quantity X bar, which is the sum of the Xi's over n, is called the sample mean. Okay, what we need to find is the expected value of the sample mean. All right. Okay, and you probably have a guess of what it will be. Each one of these guys has a mean mu, and you're adding them all up and dividing by n. For that matter, you could take the 1 over n outside. What will then this average of these Xi's have? What kind of mean? Okay, so that's easy to see. All right, so what is the expected value of X bar? Well, I'll just write it out. You have, that's the expectation, I equals 1 to n, Xi over n. Okay, 1 over n is common to all of them, so you could take it out of the sum, and it's a constant in the expectation, so you could take it out of the expectation. So that's 1 over n, oops, the expected value of sum of the Xi's. All right, okay, so what is that? That's 1 over n. Now what can you do with this? The expected value of a sum, we just saw the expected value of a sum of two random variables, x plus y. That's the expected value of x plus the expected value of y. Well, in the exact same way, I mean, over here it's just n different random variables that are independent, and they have the same distribution. So what you can do over here is the expected value of a sum. You have, this is the sum of the expectations. All right, and each one of them is mu, and you're adding them up n times, so you have n mu over here. So this result is just mu, as you expected. So the expected value of this that we call the sample mean is the same as the mean of the distribution. Okay, so the distribution for each one of them, it's the same as that. All right. Okay. Now, and this is exactly what you would think it would be. Let's look at a couple more examples. Okay, and in the next one, we'll look at random variables, and we want to find an expectation, and it's a nice, very cute application of indicator functions. Okay, where you have the random variables 1 when something occurs and 0 when something doesn't occur. Okay, we'll look at that now. I'm just going to start it on a new page. Okay, so that is example 2H. Okay, so what do you have? You have n people there. I'll read it out. Suppose that n people throw their hats into the center of a room. The hats are mixed up, and each person randomly selects one. Find the expected number of people who select their own hat. Okay, so there's n people. They all have hats. They throw them in the center of the room. Then randomly go pick one. You want to calculate the expected number of people who have their own hats. Okay, all right. So how do we approach this? Well, what we're looking for is the number of people who have their own hats. Okay, so let's call that a random variable, because of course that's random. Let x be the number of people Okay, so this is the number of people who have their own hats. All right. What do? You're going to line up all these n people and ask the first one, do you have your hat? Or do you have someone else's hat? If he says yes, he has his hat, you count him 1. Next person. Do you have your hat? Yes or no? If he doesn't, you add 0 to this one, or if he does, then you add another 1 to this one, and you'll have so far 2 people. So that's the kind of thing you can do. You can just create these indicator random variables. Okay, so suppose you let xi be equal to 1 if ith person has his own hat, and 0 otherwise, okay, then the random variable x will be what? Be x1, just like I said, that's 1 or 0. If the person has their hat, it's 1. If not, it's 0. So you're just going to be adding up the number of people who said yes, and that is just sum of x1 through xn, okay? And let's now, so you have the expected value of x will be the expected value of this sum. And we know that's the sum of the expectations. Okay. Oops. I put parentheses in the wrong places there. You don't even need to write the parentheses here. Let's just leave it like that. Okay. All right. And now let's calculate for each one of them, any one of them, what is it? E of xi. Well, what kind of random variable is xi? It is a discrete random variable. It's either 1 or 0. So this will be 1 times the probability xi is 1 plus 0 times the probability xi is 0, right? That's how you calculate the expectation of a discrete random variable. You add it up over all the values in the range of the random variable. The number times the probability, the random variable is that number, okay? And this doesn't matter. So this is the probability xi equals 1. Okay, so for any one of the people, what is the probability that he has his own hat? There's n hats, and the probability that any one of them has in his own hat will be 1 over n, correct? Okay, so just putting that in there, what is the expected value of x? You adding up 1 over n times, so it'll be n times 1 over n, and the answer is 1. Okay, now that's little surprising. You might not have expected this. No matter what, no matter how many people there are, the expected number of people that have their own hat is 1. Okay. Oh, that's I think a little bit, maybe not so intuitive a result. Okay. All right. So I hope this all is making sense. Of course, if you have any questions, don't hesitate to ask, okay? So in this case, you can say on average, one person will have their own hat. All right? Okay. And of course, you know, in small cases, you can actually exactly do the probability calculation. So suppose you have 2 people, you can find out what's the probability, what is the range then. If you have 2 people, then the number of people who have their own hat is either 0 or 2. The probability of it being 0, you can calculate. The probability of it being 2, you can calculate. Each one will be half, and the expected value of x is 2 times 1/2, and that will be 1. Okay, but this is a much more, it's a far more clever way of finding this expectation, no matter what n is. You know, that kind of breakup can get pretty tedious when you have more people with their hats. Oh, all right. Now we'll look at something that's called a random walk in the plane. All right, it's a very cute problem. Okay, so what you have in this example is, let's say you're starting at the origin. This is example 2L. All right. So in this example, what you're doing, or you have a particle. I'll just actually read out the question first. Consider a particle initially located at a given point on the plane. And suppose that it undergoes a sequence of steps of fixed length, but in completely random direction. Specifically, suppose that the new position after each step is 1 unit of distance from the previous position and at an angle of orientation from the previous position that's uniformly distributed over 0 to 2 pi. Compute the expected square of the distance from the origin after 10 steps. After n steps, sorry. Okay, so what is this problem saying? It's saying that you have a particle on the plane, and we can just assume that you're starting the particle at the origin, or call the initial position the origin, it doesn't matter. All right, so what this particle is going to do, it's going to take a step of length 1. All right, so no matter what, it can take a step of length 1 in that direction, there, anywhere. It's going to end up anywhere along this circle. Okay, after 1 step, it'll end up anywhere over here. So let's just suppose it's here. Okay, then once again, what is it going to do? And how about the choice? The angle theta is uniformly distributed from 0 to 2 pi. Okay, and the length is always 1. So once again over here, it's gonna, let's just extend this out like that. It's gonna be, angle will be anything from 0 to 2 pi, counting from the positive direction if you extend it out from the initial position, and or the previous position. And let's suppose it goes like this, for example. Okay, so it goes a length of 1, and once again, you know, you have this, oops, sorry. Okay, now once again, the angle is anything from 0 to 2 pi. I mean, in this case, I know I'm taking it this way. And you're gonna go again a distance of 1. Okay, and what you're doing is, let me mark all these in dark. Okay, so that's where you are after 3 steps. What you're asked is, find the expectation of the square of the distance from the origin or the initial position after n steps. So here is the distance after 3 steps in this drawing, and you want to find the expected value of the square of the distance. Okay, so how will we tackle this? Just looking at it like this, it seems like this very broad, open, big question. And how will we look at this? Well, what can you do? You can look at, from one step to the other, the change in position. Okay, what is the change in from one step, for example, from the first step to the second, or the second step to the third? What is the change in position? All right, so let's do that. Solution. So you let xi comma yi denote the change in position in the ith step. Okay, so this was the first step, that's the second step, that's the third step, and so on. Okay, and we want to find expected value of the distance from the initial position to the where you end up after the nth step, the square of that. Okay, so what will be xi? yi. These are random, right? What is this change in x? What's this change in y? That's random. And what is that going to be? Well, you take a look. Theta is exactly what determines what this is going to be. And what do you know about this? Well, each one of them have the same distribution. Theta is uniform from 0 to 2 pi. The distance is always 1. So you know that theta I is the angle. Let's suppose that's the angle that you have. And you're going to let, actually here, let me just write it like this. Let theta I, for I being 1 through n, be n independent random variables and all are with all of them being uniform from 0 to 2 pi. Okay, so all of these theta i's, they determine what angle you're picking on the ith step. And what will xi and yi be? Well, xi, you take a look, what will that be? That'll just be, depending on what angle you pick, that'll just be cosine theta I, correct? And yi will be sine theta I. Okay. And where will you be after n steps? So where will you be after 2 steps? What are you going to do? You're just going to take your initial, add this x1, y1. That's where you are after 1 step. Where are you going to be after 2 steps? You're going to go from here and to these coordinates and x2, y2. And that'll tell you exactly, you're going to add to x1, y1 the change, which is x2, y2. And that'll tell you where you're going to be after 2 steps. So where will you be at the end of n steps? The position after n steps will be the sum of these xi's. Okay, so that's the position of the particle after n steps. And what we want is, that's the x coordinate of the particle after n steps. That's the y coordinate of the particle after n steps. What you want is the square of the distance. Well, if you have any particle anywhere, okay, so let's suppose that's the x and y coordinate. What is the square of the distance from the origin? That's just the x squared. D squared is x squared plus y squared, right? So this will be summation xi squared plus summation yi whole squared. Okay. All right. So let's write down, what will that be? That will be, each one will have the xi squares and they'll have the cross terms xi, xj. Okay. Okay, so these are when xi times xi, and these are all the xi times xj. Okay, you can do each one of these summations separately and open it out, and this is what you will have. Okay, and then just put it together, just the common terms xi plus yi square, xi square plus yi square, and the terms with xi not I not equal to j. Okay, all right, and let's figure out, what will this be? What is xi square plus yi square? Well, you know, firstly, the distance, the jump at any point, any stage is length 1, which is why we had the xi as cosine and sine theta, but theta was the uniform one. So you know each one of these is 1. You adding up n of them, so this will be n. And then now you have I naught equal to j, xi xj, plus summation I naught equal to j, yi yj. All right. Okay, so let's write this down. N plus summation I naught equal to j. This is cosine theta I times cosine theta j plus summation I naught equal to j sine theta I times sine theta j. All right. Okay. So let's take a moment and figure out what the expected value of this is. So we want the expectation of d squared. So the expectation of d squared is the expected value of this whole thing. Okay, and expectation, splitting this up, you will have the n plus the expected value of cosine theta I times cosine theta j. And then the same with the sines. Okay. All right. So let's look at cosine theta I times cosine theta j. Okay. This is a sum. We can now, in fact, even take the sums out. And then the same with the following one. Okay, so that's what it's come down to. Now let's look at the expected value of cosine theta I times cosine theta j. Okay. Now, because of the independence of theta I and theta j, you remember from chapter 6, you have two random variables are independent. Then if you have a function g of xy, which is h of x times k of y, the expectation is just the expectation of h of x times the expectation of k of y. So this is just the expectation of cosine theta I times the expectation of cosine theta j. Okay, and the same with the sine. So we just need to calculate each one of these. What is the expectation of cosine theta I? All right, well, what is this? Theta I is uniform from 0 to 2 pi. So let's just put that in. Put in the density 1 over 2 pi. And we'll put in cosine theta I d theta I. Okay. All right, or maybe we shouldn't use that letter. Let's use a different one. Let's use t. Okay. All right, so what is this integral? That's 1 over 2 pi integral. That's sine t from 0 to 2 pi. And sine 2 pi minus sine 0, that's just 0. So this is 0. All right, so each one of these, in fact, will be 0. And similarly, you have the expected value of sine theta I. That's 0 to 2 pi, 1 over 2 pi, sine t dt. Okay, and what is this? 1 over 2 pi. Integral will be minus cosine t from 0 to 2 pi. And once again, you plug all this in and you get 0. So each one of these expectations are 0. So you do finally have that the expectation of d squared, which we saw was n plus summation I not equal to j expectation of cosine theta I, cosine theta j, plus summation I not equal to j expectation of sine theta I times expectation of sine theta j. Each one of these is 0. So you have that the expected value of d squared is in fact n. All right. So the expected distance you are from the initial position after n steps, expected value of the square of the distance that you are from the initial position after n steps is in fact n. Okay. All right. Well, I hope these variety of examples made sense to you and that you're able to use these techniques to find to solve the homework problems as well as other kind of expectation problems that you might have. Okay. This indicator variable, the indicator random variable property, that's very nice to use many times when you're counting. That's a good way to do it. Breaking up a problem into what aspects you have. You know, distance is not changing. Okay, so you are ending up on a circle of radius 1. Okay, so then you use cosine and sine, those kind of things. Using that, it makes many of these problems much easier. All right, guys. Well, I hope that made sense. And as usual, please ask if you have any questions. Even when you're doing the homework, email what questions you have, and we can make a video of the solutions. All right, so next we will look at 7.4, okay? But this is all for 7.2. All right, bye, guys.